Why is ice slippery? That sounds like a question you already know the answer to. You've heard it since school. There's water on the surface. The ice melts a little. The water acts like a lubricant. End of story. Except that explanation is wrong. Or at least, it's incomplete in a way that should bother you. Because it explains something you see, but not something you experience. And when you dig into what's really happening when your foot slides across ice, you discover that slipperiness has almost nothing to do with melting, and everything to do with how nature behaves at the edge of order. Let's start with what feels obvious. You step onto ice, your foot slides. There's little friction. That's what slippery means. If you step onto rough concrete, your foot grips. If you step onto ice, it doesn't. So what's different? The usual answer is that ice melts under pressure. Your weight presses down, the ice warms slightly, a thin layer of water forms, and that water lets you slide. It sounds reasonable, it sounds clean, but it falls apart almost immediately. Because ice is slippery even when it's far below freezing, even when the temperature is so low that pressure melting is negligible. Ice rinks work in cold arenas. Frozen lakes are slippery at temperatures where melting is effectively impossible. And even more unsettling, ice is slippery when nothing is pressing on it at all. A hockey puck slides before a skater ever touches it. Ice is slippery to objects that aren't warm, heavy, or capable of melting it. So if melting were the real reason, slipperiness would disappear in extreme cold. It doesn't. So something else is going on. To understand it, you have to stop thinking about ice as a solid block and start thinking about it as a structure, one that is almost, but not quite, stable. Ice is a crystal. That means its molecules are arranged in an orderly pattern. Water molecules lock into a lattice, each one held in place by hydrogen bonds. Those bonds are strong enough to keep the structure intact, but weak enough to be on the edge of breaking. That edge matters. Inside the ice, molecules are locked in. They vibrate, but they can't move freely. That's what makes ice solid. But at the surface, things are different. A molecule at the surface is missing neighbors. It isn't fully surrounded. Some of its bonds are broken simply because there's nothing there to bond with. That makes the surface molecules less constrained. They're still part of the ice, but only barely. This means the surface of ice is not really solid in the same way the interior is. It's more like a constantly shifting boundary where molecules are half free, not liquid, not solid, something in between. This layer exists even when the temperature is far below freezing. It's called a quasi-liquid layer, but the name doesn't really matter. What matters is what it does. Those surface molecules can rearrange easily. They can slide past one another with very little resistance. And when something touches the ice, your foot, a skate, a puck, it interacts with that boundary layer, not the rigid crystal underneath. So the slipperiness of ice is not mainly caused by melting. It's caused by the fact that ice never truly has a rigid surface. It always has a thin, dynamic layer where molecules are on the verge of freedom. Now think about how strange that is. The very thing that makes ice solid, its ordered structure, also guarantees that its surface can never be perfectly solid. Order creates its own weakness at the boundary. Nature doesn't allow sharp edges between states. There are always transitions, always gradients, always regions where definitions blur. And ice happens to live right at one of those borders. This also explains something you've probably never questioned. Why is ice more slippery than most other solids? Metal is smooth. Glass is smooth. Polished stone is smooth. but none of them are as slippery as ice. That's because most solids have surfaces where atoms are locked in place. Even if they're smooth, the atoms can't easily rearrange to accommodate motion. They resist being sheared. Ice doesn't resist in the same way. Its surface is already unstable, already flexible, already on the brink of becoming something else. So when you slide across ice, you're not gliding over a hard surface lubricated by water. You're interacting with a layer of molecules that are barely holding on. Friction is low because resistance is low, not because something is melting away, but because the surface never fully commits to being solid. Now here's where this becomes uncomfortable, because the same explanation applies even when the ice does melt a little. Pressure and friction can add energy. That energy can thicken the surface layer. It can make it more liquid-like, but that's a secondary effect, not the cause. The cause is structural. Ice is slippery because its molecular bonds are arranged in a way that makes the surface inherently unstable. And that instability is not a flaw, it's a consequence of water itself. Water is strange, you already know that. It expands when it freezes. It has a density maximum. It behaves differently from most liquids. All of that comes from hydrogen bonding. Those bonds are directional, flexible, and just strong enough to create order, but not strong enough to lock things permanently. So ice inherits that delicacy. It's solid, but only barely. Stable, but only just. Ordered, but with constant motion lurking underneath. And slipperiness is the macroscopic signature of that microscopic balance. Now ask yourself something. If ice is slippery because its surface is never fully solid, then what does that say about solidity itself? What does it mean for something to be solid if its surface can behave like a liquid without actually melting? The answer is unsettling. Solidity is not absolute. It's statistical. A solid is not something where everything is fixed. It's something where most things are fixed most of the time. At boundaries, that certainty breaks down. Ice simply makes that breakdown obvious. You don't slip on ice because it's wet. You slip because order is fragile. And once you understand that, ice stops being just a nuisance on the sidewalk. It becomes a lesson in how nature really works, right at the edge between states. Once you stop blaming melting for slipperiness, the whole phenomenon becomes much more revealing. Because now you're no longer asking a narrow question about ice. You're asking a broader one about how matter behaves when it's almost, but not quite, locked in place. Think about friction in general. Friction is not a force that exists on its own. It's what happens when two surfaces try to slide past each other. And their microscopic structures resist that motion. Atoms snag. Bonds stretch. Energy gets shuffled into vibrations. And heat. High friction means lots of resistance at the microscopic level. Low friction means very little. So why does ice offer so little resistance? Because the molecules at its surface don't snag very well. They don't hold on tightly. They rearrange instead of resisting. When your foot tries to slide, the surface doesn't fight back. It yields. That yielding is the key. Most solids resist shear. Ice doesn't, at least not at the surface. Its hydrogen bonds are constantly breaking and reforming, even at low temperatures. The surface is alive with motion. This is not something special your foot creates. It's already there. Now consider something even stranger. Ice is slippery, not only to warm objects, but also to cold ones. A steel skate at sub-zero temperatures glides effortlessly. A frozen puck slides across a frozen lake. There's no heat exchange to speak of. No significant melting. And yet the slipperiness remains. So the explanation has to work without invoking warmth or pressure. And it does, because the surface layer is not a result of melting, it's a result of broken symmetry. At the surface, molecules lack neighbors. That lack changes everything. Bonds that would be satisfied in the interior are left dangling. The molecule compensates by fluctuating more, exploring more configurations. This is not liquid water, but it's not solid ice either. It's a compromise. Nature loves compromises. This surface layer is thin, only a few molecules thick, but that's enough. Because friction is a surface phenomenon, what happens deep inside the ice is irrelevant to how slippery it feels. You don't interact with the bulk. You interact with the boundary. And boundaries are where physics becomes interesting. At boundaries, definitions soften. Solid becomes almost liquid. Fixed becomes flexible. Order becomes negotiable. This is true not just for ice, but for many systems. But ice sits in a very special place. Water's hydrogen bonds are weak enough to allow this quasi-liquid behavior even far below freezing. If water's bonds were slightly stronger, ice would be rigid at the surface. It would grip like rock. Skating would be impossible. Winter would feel very different. If they were slightly weaker, ice wouldn't exist at all. So ice's slipperiness is not an accident. It's a consequence of water being tuned just right. Now let's push this idea further. If slipperiness comes from surface instability, then adding energy should enhance it. And that's exactly what happens. When you skate, friction generates heat. That heat thickens the surface layer. It makes it more liquid-like. Slipperiness increases. The skate glides even more easily. But notice what's important here. Heat doesn't create slipperiness. It amplifies something that already exists. This is why the melting explanation feels tempting but incomplete. It describes a feedback mechanism, not the root cause. The root cause is structural. Ice is already halfway to being liquid at its surface. You're just nudging it along. Now think about why this explanation feels uncomfortable. It tells you that states of matter are not as cleanly separated as you were taught. Solid, liquid, gas, they sound like distinct categories. But in reality, they blur into one another at the edges. A solid can have a liquid-like surface. A liquid can have solid-like order locally. A gas can behave collectively like a fluid. These are not exceptions. They are the rule. Nature does not draw sharp lines. It draws gradients. Ice is slippery because it lives on a gradient, right at the boundary between order and freedom. And here's where this connects back to Feynman's way of thinking. The most powerful explanations are not complicated. They don't pile on mechanisms. They strip things down to what must be true. Ice must have surface molecules that are less constrained. Less constrained molecules must rearrange easily. Easy rearrangement means low resistance to sliding. That's it. No mystery. No hidden trick. Just structure and consequence. And that's why the explanation feels uncomfortably simple. Because once you see it, you realize there was never anything else it could have been. Now ask yourself one more question. If ice is slippery because of how water molecules bond, what else in the world behaves strangely for the same reason? The answer is a lot. The peculiar properties of water, its expansion on freezing, its high surface tension, its ability to dissolve so many substances, are all consequences of the same delicate bonding, and those properties shape the world far beyond ice. They shape climate. They shape biology. They shape life. The fact that ice floats keeps lakes from freezing solid. The fact that ice is slippery allows glaciers to flow. The fact that water forms flexible networks allows cells to function. A tiny detail at the molecular level cascades upward into planetary scale behavior. Ice slipping under your feet is a reminder of that cascade. You're not just sliding on frozen water. You're interacting with a balance of forces that makes Earth habitable. Now pause and think about this. If ice behaved like most solids, winters would be brutal in a very different way. Glaciers wouldn't move. Ice sheets wouldn't reshape landscapes. Life might never have survived long enough to evolve. Something as mundane as slipping on ice is tied to the deep physics of hydrogen bonds and surface energy. That's the part that should stay with you. Ice is slippery not because it's wet, but because it's delicate. Because its order is always negotiating with disorder. Because nature rarely commits fully to one state. And once you see that, the sidewalk in winter stops being just a hazard. It becomes a demonstration. Once you understand that ice is slippery because its surface never fully settles into solidity, a deeper pattern starts to emerge. Slipperiness stops being a quirky property of frozen water and starts looking like a window into how matter behaves when it's balanced on a knife edge. Most materials are not balanced that way. Their atoms lock into place and stay there. Even when they vibrate, the vibrations are small. The structure resists change. That resistance is what you feel as friction. Ice is different because its structure is under tension from the moment it forms. When water freezes, the molecules arrange themselves into an open lattice. That lattice is stable, but only because each molecule is held in a careful compromise between attraction and repulsion. It works, but just barely. That barely matters most at the surface. At the surface, molecules are exposed. They have fewer neighbors to stabilize them. The same hydrogen bonds that hold the crystal together also make the surface restless. Bonds break, reform, stretch, and rotate. Nothing is rigid for long, so when something tries to slide across ice, the surface doesn't oppose that motion in the usual way. It doesn't dig in. It doesn't catch. It adapts. And adaptation kills friction. Friction comes from resistance. Resistance comes from rigidity. Ice's surface lacks rigidity by design. This is why ice feels paradoxical. It looks solid. It is solid. And yet it behaves like it's almost not. Now consider something you might not have thought about. If you polish a piece of metal until it's perfectly smooth, it still won't be as slippery as ice, even though the metal might look smoother to your eye. That's because smoothness at the human scale is irrelevant. What matters is smoothness at the molecular scale, and metal atoms don't rearrange easily. They sit in a rigid lattice with strong bonds. When you try to slide, those atoms resist. They push back. Ice's atoms don't push back in the same way. They slide past one another. They reorganize. They dissipate energy differently. So slipperiness is not about smoothness. It's about compliance. Ice is compliant at its surface. Now let's make this even more uncomfortable. If ice is slippery because its surface is unstable, then slipperiness is not a special property of ice at all. It's a general consequence of being near a phase transition. Any material near the boundary between solid and liquid will show similar behavior under the right conditions. Ice just happens to sit unusually close to that boundary over a wide range of temperatures. That's why this explanation generalizes so well. It doesn't rely on ice being cold or wet or under pressure. It relies on ice being almost something else. That's the real secret. Ice is slippery because it is always on the verge of becoming liquid, without actually doing so. And that idea echoes something much bigger in physics. Many of the most interesting phenomena happen near transitions, near tipping points, near boundaries between order and disorder. Superconductivity, magnetism, phase changes, critical behavior. At those edges, systems become flexible, responsive, strange. Ice is one of the simplest examples you encounter in everyday life, but it's governed by the same principles that drive far more exotic effects. Now think about how counterintuitive this is. You would expect the coldest surfaces to be the most rigid, the most resistant, the least slippery. But ice defies that intuition. It becomes slippery not in spite of being cold, but because of how cold organizes water molecules. Cold locks them into a structure that is inherently fragile at the boundary. That fragility is what you feel under your feet. So when Feynman talks about ice, he's not interested in ice itself. He's interested in what ice teaches you about explanations. A good explanation doesn't just tell you what happens. It tells you why nothing else could have happened. Ice must be slippery because of how water molecules bond. If they bonded differently, ice wouldn't behave the way it does. And if ice didn't behave the way it does, large parts of the natural world would be unrecognizable. So a simple question, why is ice slippery, opens the door to something much larger. It shows you that the properties you take for granted are not arbitrary. They are consequences of deep structure. It shows you that everyday experience is shaped by microscopic compromises. And it shows you that simplicity in physics is often uncomfortable because it strips away stories you've grown attached to. Melting feels like a story. Pressure feels like a cause. But structure is the truth. Ice is slippery because its surface is never fully solid. Because order is weakest where it meets emptiness. Because water's bonds are strong enough to hold and weak enough to give. Once you see that, you stop slipping on ice without thinking. You notice it. You realize you're standing on a boundary where matter can't quite decide what it wants to be. And that realization changes how you see not just ice, but solidity itself. At this point, the explanation has done something subtle to you. It has taken a familiar experience, slipping on ice, and quietly removed the story you thought explained it. In its place, it has left something simpler and far less comforting, because now you know that ice is not slippery due to an accident of temperature or pressure. It's slippery because solidity itself is not what you imagined it to be. You were taught to think of solids as fixed, locked, rigid. But ice shows you that rigidity is not absolute. It's conditional. It depends on how atoms are arranged, how bonds behave, and what happens at the edges. Inside the ice, order dominates. At the surface, order weakens. And it is always at the surface where reality reveals its true character. That's a pattern you'll see everywhere once you start looking for it. Surfaces are where things happen. Interfaces, boundaries, places where rules overlap instead of cleanly separating. Ice is slippery because its surface lives in that overlap, between solid and liquid, between order and motion. And here's the part that should really stay with you. The slipperiness of ice is not a flaw in nature's design. It's a consequence of balance. Water molecules bond just strongly enough to form structure, but not so strongly that the structure becomes brittle and dead. That balance is what makes water adaptable, and adaptability is what life depends on. So when you slip on ice, you are encountering the same delicate physics that allows rivers to flow, cells to function, and climates to regulate themselves. That thin, unstable surface layer is not just a curiosity. It's a signature of a universe that prefers flexibility over rigidity. Now think about how different the world would be if ice behaved like stone. If frozen water gripped instead of yielded, glaciers would grind to a halt. Ice sheets would lock landscapes in place. Seasonal cycles would change. Ecosystems would struggle. The slipperiness of ice is not a nuisance. It is a necessity. And that brings you back to why this explanation feels uncomfortably simple. Because once you see it, there is nothing left to argue with. No missing piece. No hidden mechanism waiting to be discovered. Ice is slippery because its surface molecules are less constrained. Less constraint means easier rearrangement. Easier rearrangement means low friction. That's the whole story. It doesn't rely on special conditions. It doesn't fall apart in extreme cold. It doesn't depend on pressure or heat as primary causes. It works everywhere ice exists. And that's why it's a good explanation. Feynman cared deeply about explanations like this. Not because they were clever, but because they were honest. They didn't decorate reality, they revealed it. They showed you that the world behaves the way it does not because it's trying to be helpful or intuitive, but because of how its pieces must fit together. Ice doesn't know it's slippery. Water molecules don't aim to make skating possible. Nature doesn't optimize for convenience. It simply follows its structure. And from that structure, everything else follows. So the next time you step onto ice, notice what you're really standing on. Not just frozen water, but a boundary where order weakens, where bonds fluctuate, where solidity becomes negotiable. You are standing on a reminder that even the most familiar things are held together by compromises. And once you see that, the question, why is ice slippery, stops being a trivia question. It becomes a lesson about surfaces, about boundaries, about how the simplest experiences are often governed by the deepest rules. And if you let that lesson sink in, you start to see the world a little differently, not as a collection of rigid things, but as a network of structures constantly balancing on the edge of change. If this explanation surprised you, comment ice below. I want to know which part changed how you think about something so ordinary. If you enjoy seeing simple questions lead to deep physics, subscribe.